Now let's consider the total number of subsets in any one set, because when we're choosing some items out of a bigger group of items, basically by making a subset. Now, we'll need to consider subsets of all different sizes. So, again, let's start with an example. How many subsets can we make from a set of letters, only 5 letters, A, B, C, D, and E? Well, we'll need to consider the size. Can we make a set that has nothing in it? Yes, we can. How many of them would there be? Well, there's just one. Can we make a set that just has one letter in it? Sure. How many different ones would there be? Well, it could be just A, just B, just C, just D, or just E. So there's 5 different ones that would look like that. Now, coming down the other way, we're looking at complements now. If there's only one set we can make that has nothing in it, then there's also only one set that we can make that has all 5 of those letters in it. And if we're going to choose a set of 1, isn't that effectively the same thing as choosing to leave the other 4 out? So if we're thinking how many different ways we can select 4 out of the 5 letters, we could either leave out the A, leave out the B, leave out the C, leave out the D, or leave out the E. So we can see here that what we've just considered, that 5 choose 0 is going to be the same as 5 choose 5. And 5 choose 1 is going to be the same as 5 choose 4. Now we've taken a bit of the hard work out of it, we can see that we only need to find one of these and we'll have the other. We've also got our method here, 5 choose 2. Now, we actually thought of all of the ways we could choose 2 letters out of 5 earlier. We could have A with B, C, D, or E. That's 4 different combinations. Or we could leave the A out, start with B. We've already considered B with A. We can't have B with B, so we'd need to have B with the C, D, or E. And then the C with the D or the E, and then the D with the E. So there's 4 plus 3 plus 2 plus 1. Now that looks a bit like a factorial, doesn't it? But it isn't. It's just adding. It's not multiplying. But there's 10 ways, and you can verify that by putting in 5 choose 2 into your calculator and seeing there's 10 ways that you can choose 2 letters out of the 5. And that should be exactly the same as the number of ways that you can choose 3, because choosing 2 is effectively choosing to leave out 3, and in fact that's making a set every time you do that. Now if we add these up, then the total will come to 32. Now we've got 5 letters and we've chosen 2, and the answer is 32. Is this setting anything off for anybody? How are 2 and 5 related to 32? Well, could it be related that we have 2 to the power of 5? Or is that just a coincidence? It is actually not a coincidence. 2 to the power of 5 is, there's a good reason why that's the total number of subsets. Now, what we can do here is we can consider that as we were trying to make subsets, imagine if we saw each of our letters just as a chance to either take it in the subset or not. Well, here, when we made our subset that had nothing in it, it's almost like we said, well, we'll choose yes or no to everything. And we said, we'll have no for the A, no for the B, no for the C, no for the D, and no for the E. 5 no's in a row. Whereas when we chose to make a subset with 1 in it, it could either be yes, no, 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 or no, yes, no, no, no. Or we could put the yes third, or we could put it fourth, or we could put it fifth, depending on which one we said, yes, we'll put that one in. Now, if we break this down into a series of saying yes or no to each element that we can choose from to decide whether or not we could put it in a set, this 2 to the power of 5 makes a lot of sense. Why? Well, if you can only choose yes or no, you've only got 2 items you can pick, and you're picking it 5 times, then it makes sense that there's 2 things you could have, times another 2 things that you could have, times 2 things you could have, times 2, times 2. And that gives us our 2 to the power of 5. So it's no coincidence that we've ended up that way. Now the other thing that we can see here is that if we add all of these together, we should get this number. So we can write that out now as a bit more of a formal rule. Then we can say that if we've got some set that contains n items, then if we have n choose 0 plus n choose 1, n choose 2, etc., all the way up to n choose n, what we'll get as the total number of subsets is 2 to the power of n. And now perhaps it's easier to see what we were referring to last lesson when we were dealing with identical items and we only had 2 of them and we were looking at ordered selections. Because what we said was, if we had only 2 items, and remember we had the example of the tumblers and the wine glasses that we were arranging on the shelf, then if there are only 2, then we had a situation that the total number of permutations had to be divided by the number of identical items of one sort. And if you have one sort and there's only 2 sorts, then the other sort is automatically however many of these there are, total, minus however many of those there were. And we came up with this formula to decide that there were this many permutations when we were arranging those 2 different types of glasses. Now this is the same as the n choose r formula. So now we can perhaps see why. So when we're looking at something like 5 choose 2, and we're choosing 2 items out of 5, it's as though we've said yes to 2 of the items and we've said no to 3 of them. Now if you look at all the ways that you can arrange yeses and nos in a row, then if there's 5 of them, you'll say there's 5 factorial ways to arrange all the yeses and nos. But you'll also say, hold on, if 2 of the items are both yes, they both look the same, so we've got to divide by that because we've counted them twice. And if 3 of the items are no's, they're all identical, so there's 3 factorial ways those can be arranged. And we could have come up with that answer. Now you don't need to go back to this thinking of yeses and no's when you're looking at combinations, but I think it is important to recognise that this same situation occurs when we've got ordered items and 2 of them, and they're identical, as what it does when we're choosing combinations that actually don't have any order.